Now we are going to see the experiment design and testing of RC phase shift and Wein bridge oscillator using operational amplifier. Our aim is to construct the RC phase shift oscillator as well as Wein bridge oscillator, which can generate the sine waveform using operational amplifier without giving any input signal. These are the components required for designing the circuit: resistance, capacitance, operational amplifier, CRO to see the output, and RBS for power supply of the operational amplifier. RC phase shift oscillator. RC phase shift oscillator is nothing but an oscillator circuit which is designed out of operational amplifier as well as a stage of RC network. It consists of two stages. The first stage of operational amplifier will produce the 180-degree phase shift, and the second stage, which consists of RC network, three combination of RC, which produce another 180-degree phase shift. Therefore, there will be a zero phase shift at the output. Therefore, we will get a sinusoidal waveform which is generated by means of this RC network and operational amplifier. Without giving any input, we just produces the sinusoidal waveform. This is called as oscillator. And the RC phase shift oscillator frequency is noted as f not equal to 1 divided by root of 6 into 2 pi RC. The gain should be always approximately equal to 29. Therefore, the condition for design is RF should be greater than or equal to 29 R1. Taking into this consideration, we are going to design the RC phase shift oscillator. Setting the frequency and the capacitance value, we are going to find the value of resistance, and we are going to design. Keeping off F naught is equal to 500 Hz and C equal to 0.1 microfarad. We have to calculate the value of R. We obtained R is equal to 15K. To prevent the loading, the condition for calculating R1 is R1 should be greater than or equal to 10 R. Therefore, R1 is equal to 150 kilo. From this condition, we can obtain the value of RF. RF is equal to 4.35 mega. Using these parameters, we can design the RC phase shift oscillator, substituting the RC values, R1 values and RF values here, and we have drawn the circuit diagram for this RC phase shift oscillator. We are going to simulate this RC phase shift oscillator using multisim software. Now we are going to see the output of this RC phase shift oscillator and Wein bridge oscillator. This is the output for the RC phase shift oscillator. Sine wave is generated. We have to note the voltage, time as well as the frequency. Similarly, we are going to see the Wein bridge oscillator. This is a Wein bridge oscillator. It consists of operational amplifier and the RC network. This is a RC network, and this is a Wein bridge network, and this is the output network. This output network provides 180-degree phase shift, and this Wein bridge network series and parallel combination of R and C produce 180-degree phase shift. Without any input, we get the output as a sinusoidal waveform. So it is called as oscillator. In oscillator, generally we are using positive feedback, whereas in amplifier we will use the negative feedback. This is the output of the Wein bridge oscillator and the graph which we will draw. Regarding the Wein bridge oscillator, here the frequency f naught is equal to 1 by 2 pi RC. The design procedure is, here we have to use the formula f naught is equal to 0.65 into RC. 1 by 2 pi is equal to 0.65 divided by RC. We are going to take the value of C and obtain the value of R, and we have to calculate the value of R1 as well as RF. Using these values, we are going to draw the Wein bridge oscillator circuit diagram, and we are going to simulate in the multisim software. Okay. See, this is the output for RC phase shift oscillator, and using multisim live, I have shown the RC phase shift oscillator output. This is the RC phase shift oscillator. You can see the RC phase shift oscillator using this multisim live. You can draw the schematic using this component and connecting together. See, this is the RC network. Three RC network combined together and it produces 180-degree phase shift. And this is an operational amplifier with feedback resistance as well as input resistance. We have not given any input voltage or any frequency. The frequency is generated internally using this RC network and it produces an output. At the sixth pin, we are taking the output and the sixth pin produces the output as a sinusoidal waveform. See here the sinusoidal waveform is generated here completely at the output V0, where the R3, that is at this node the voltage V is lightly generated in the green color. At this node the voltage is generated by some oscillation, and at this node the voltage is generated somewhat, and after entering into this operational amplifier combination it will produces a perfect sinusoidal waveform. This is the oscillation which we produce, we obtained at the RC phase shift oscillator. This is the output of the RC phase shift oscillator. Now I am going to simulate and you can clearly see the simulation output. This is the live output for the Vane bridge oscillator. This is the diagram for the Vane bridge oscillator. Here the op-amp produces 180-degree phase shift, and this RC network series parallel combination is the Vane bridge network which produces 180-degree phase shift, and it generates a sinusoidal waveform at this output B not called an oscillator. The oscillator is a positive feedback and we will never give any input for this operational amplifier network, but it produces an output as a sinusoidal waveform which is called as oscillator. Now you can see the output of the oscillator in this simulation window. See how the sine wave is generated and it produces a continuous oscillation. Now we can simulate and we can see the this is schematic and this is the grapher. We can see combined combination of this schematic and the grapher. You can simulate by click this run button. You can also change the values of RC parameters. See, you can get the output of this oscillator. This is the output for the Vane bridge oscillator. You can change the values of capacitance, resistance, and we can also control the voltage of the oscillating output. We can change the height as well as width of the scale in the graph by clicking this voltage source and click on the graph, so that you can change the time period as well as voltage. Minimum time period -16, maximum time period 4.4. Also time scale can be adjusted 93 to 102 there. Similarly, you can see here we are giving the voltage knob at this terminal PR1, therefore we are given plot PR1. If we assign some other voltage source at this particular terminal, what will be the then it will also appear. You can also give particular value to that particular voltage, and we can simulate the output and see the voltage. Okay, see while simulating you can see the read the voltage output in this terminal. See, -11.789 volt is the output voltage which we obtained in this oscillator circuit. Thank you.